Okay, I decided for us to go ahead and finish up this section today, so we won't have everything piling up on Monday. We need to finish example 6. That's where we left off at the end of class today. Example 6 says to find all the zeros of this particular function. Remember that since I'm recording this, you can always pause and replay it or stop it till you copy things down or whatever. So it says that 2 plus I is a 0, and we're supposed to find all the zeros. So if 2 plus I is a 0, when I do synthetic division, my remainder will be 0. And that will break it down to a lower degree polynomial that I can do again a division until I get done. If 2 plus I is a 0, then I also know that 2 minus I is a 0, which will make it down to a second degree equation because it's a fourth degree equation. The equation says f of x is equal to 1x to the fourth minus 1x cubed minus 17x squared plus 55x minus 50. And I've left myself plenty of room because I'm doing a complex number here and I'll have to multiply that out. Okay, so I bring down the 1 and I take 2 plus I times 1, which gives me 2 plus I. And I add the real part. Negative 1 plus 2 is 1. And bring down the I. Okay, now I have to multiply 1 plus I and 2 plus I. I'm grabbing a piece of notebook paper. I'm going to just work it over here. I have to take a 2 plus I and multiply it by a 1 plus I. Okay? And when I do that, first times first gives me a 2. Last times last, I always do that first with complex numbers because that will give me I squared, and I squared is negative 1. On the outside, I have a 2I. On the inside, a 1I, which gives me 3I. So this is really a 1 plus 3I. Okay? So I'm going to put that here. 1 plus 3I is the result of multiplying those two. Add this together. That gives me a negative 16 plus 3I. Just add the real parts together and the complex together. But there's only one complex. Okay, and now we are going to take negative 16 plus 3I. Grab my paper here. Negative 16 plus 3I. And multiply it by the 2 plus I. Okay. So first times first gives me negative 32. Yes. Last times last gives me 3I squared. I squared is negative 1, so that's negative 3. On the outside, I get a negative 16. Nope, 16 times I, yep. And on the inside, a positive 6I. And so that combines to a negative 35 minus 10I. Looks good to me. Negative 35 minus 10I. Negative 35 minus 10I. That's the result of multiplying those. Now I add things. 55 minus 35 is 20 minus 10I. Okay, now I multiply 2 plus I multiplied by 20 minus 10I. Ugh. Okay, first times first is 40. Last times last is 10I squared, which is positive 10, negative and negative. And then on the outside I have a negative 20I, and on the inside a positive 20I. How handy is that? That gives me exactly 50. Okay, and my remainder is 0, and we knew it would be 0 because they said it is a 0. So why is 0 at that point? Okay, now we know that these are the numbers that go in front of the polynomial. We'd have 1x cubed, 1 plus ix squared. We don't need to write that down. We also know that 2 minus I has to be a 0 because of what's left, because they come in pairs, the conjugates. So I'm now taking what's left here. That's right here. That's the polynomial after we divided out one of the zeros. And I'm going to do the conjugate into this. Okay, no big deal. 1, 2 minus I. This is kind of good because we have real parts to add. And, no i's left. Now I take 3 times this. That'll be 3 times 2 is 6. 3 times that, negative 3i. Add it up and I get, each time I keep getting no i's, right? That's kind of nice. 10 times this gives me negative 20 minus a negative is positive 10i. Add those up and 0, which we knew it was a 0. So now we're down to, we started with a fourth degree. We divided by x. That got to third degree. Divided by x again, second degree. So this is 1x squared plus 3x minus 10. All right, and that factors pretty easily just by inspection, or use your calculator if you want. Positive 5 and negative 2 looks like it. So if positive 5 is the factor, negative 5 is the zero. Positive or minus 2 here means positive 2. So the question said, what are the zeros? Always make sure you answer the question when you're done. 2 plus I is a 0. 2 minus I is a 0. Negative 5 is a 0. And 2 is a 0. Okay, that's the set of zeros for this problem. And there's no surprise here that we have 4 of them, right? Because it was a fourth degree equation, which means we could have at most 4. All right. One more little topic in this section, and that is Descartes' rule of signs. What is this underneath here? Oh, I'll show you that in a minute. Descartes' rule of sign. Okay, I'm going to tell you how to fill in the blank, and then I'll explain it as we work a problem. Let f of x define a polynomial function with real coefficients and non-zero constant term with terms in descending powers of x. So I've got a regular old polynomial in descending order. Part A, the number of positive real zeros. In other words, solutions that are real numbers that are positive real numbers, okay? The number of these positive real zeros of f either equals, so the first blank should be equals, the number of variations in the sign occurring in the coefficients of f of x, or is less than, those are the next blanks, less than the number of variations by a positive even integer. Okay, let's go ahead and do example 7, the first part, and do what we just filled in the blank on, and then I'll do the second part. I'm copying this polynomial. And I barely ran onto the page there. And it says, determine the different possibilities for the number of positive, negative, and non-complex real zeros. Non-complex real zeros. So we're doing the real zeros. First, we're doing the positive. Part A above in the definition said that the number of positive real zeros will either equal to the number of sign changes or be less than the number of variation by a positive even integer. So first of all, let's count how many times the sign changes. It changes from negative to positive. There's the first one. It changes from positive to negative. Second time it changes. Negative to positive, and then positive back to negative. 4 times the sign changes. We have 4 sign changes. So f of x has either 4, and you go down by 2 each time, 2 or 0 positive real zeros. Doesn't tell us a lot. It just tells us that when we go to graph this, it could have, in terms of positive real zeros, positive numbers that intercepts, right? It could have either 0, 2, or 4. And the reason for that is a little difficult to explain at this point because we haven't done the behavior of even and odd functions. That's coming up, so this is going to make a little more sense later. But for now, you're just going to have to accept that when the sign changes, count those. That's the most of the real positive zeros you can have, or subtract 2 from it to get the other possibilities. So this will either have 0, 2, or 4 positive numbers that will intercept or give us 0. Okay. Part B. Now let's fill in the blank at the top. The number of negative real zeros is either equal to the number of variations. So we put equal again. It either equals the number of variations in the sign occurring in the coefficients of f of minus x, or it is less than the number of variations by a positive integer. So it's the same thing for the negative real zeros, except we put a minus x into the function. So go ahead and substitute negative x all the way through here. Negative x squared will still be positive, so that's still a negative 2x to the 4th. Negative x cubed will be negative, so this becomes a negative 3x cubed. Negative x squared will be positive, so that leaves that the way it is. So the even ones are staying the same and the odd ones are changing. Negative x times 4 is a negative 4x. And the minus 1, of course, changes. How many sign changes do we have when we do f of minus x? There are no sign changes. So there are no negative real zeros. So what would it be in this case if we had 4 real intercepts? Then we know this thing would squiggle around and hit the x-axis 4 times. If we only had 2, then there are still 2 solutions that we need to account for in this. And those 2 would be the complex conjugates. So you would have 2 real positives and 2 complex conjugates. If you had no real solutions and we have no real positive solutions and we have no negative real zeros, no negatives or positive real number solutions, then all 4 solutions would have to be complex, okay? And they come in pairs. And again, we're going to work a lot more with this. Right now, you need to be able to use this to count how many possible solutions you have that would be real positive zeros or real negative zeros, okay? I hope that makes sense. Email me if you have a question. I can probably take a question or two over the weekend as I'm recuperating, or we can begin next class by doing those. It's helpful for me to see your questions ahead, though, because I can often answer it a little more efficiently that way. So please complete all the homework for 3.3 before Monday. And then on Monday, we will resume with 3.4 and stay on schedule. Okay? Have a good weekend. Talk to you later. Bye.